All right, now we're going to talk about vision, okay? Squarely into the sensation side of things to start. So when it comes to seeing, basically our eyes respond to some of the waves on the electromagnetic spectrum, if you will, electromagnetic radiation. Okay, so as we go from very, very short waves to longer and longer waves, okay, electromagnetic radiation in terms of uh, the lengths of the wavelength, if you will. It's this part, okay, this little uh, part here, this spectrum, okay, that's the part of the spectrum that's visible to human beings, okay. And our brain turns these energy wavelengths into colors. Okay. Um, so basically, we perceive the wavelength, the frequency of the electromagnetic waves as color. Okay. So shorter wavelengths, okay, higher frequency. That's the blue side of the spectrum, okay, and the longer wavelengths, the low frequency. And this is where we get to our reddish colors. Now, in terms of the intensity or brightness of the color, okay, so wavelengths that have greater amplitude, okay, a bigger wave, if you will, okay, not in terms of length, but in terms of height, okay, that would be associated with bright colors. Smaller amplitude would be associated with duller colors. So here's the eye, okay, it's a cross section. I just took your eyeball basically and just cut right through the middle of it. And so we're looking at a cross section on one end of it. So this is the back of the eyeball, okay, and of course this is the front. Okay, there's the pupil. So the light from the candle, okay, passes through the cornea, okay, and the pupil, okay, and gets focused, okay, and inverted by the lens, okay. So the lens, so when people have cataract surgery, basically it involves removing the lens because the lens has gotten all cloudy and um, and making it difficult to see, makes everything seem dark. And so the surgery for that is to replace the lens with a little plastic, um, malleable plastic lens. In any case, so it gets inverted by the lens, okay, and so the light, okay, the sun then gets lands on the retina. So we got actually light getting through here through the pupil, and and then inverted by the lens and going through the vitreous humor, this whole middle part, and it gets to the retina. Okay, and here at the retina is where the process of transduction into neural impulses to be sent out to the visual cortex, the occipital lobe. This is where that whole process begins, and we would see the neural impulses being carried by bundles of nerves that basically form the optic nerve, and which goes to the brain's visual cortex. Okay, the center of the retina is called the fovea, and we'll have more on that in a minute. The retina is everything, at the back of the eye, from the top all the way to the bottom, okay, with the fovea, the point where we can get our best visual acuity, being in the middle. Okay, the lens is not rigid. This is something that'll be important when we talk about depth perception. The lens can perform what's called accommodation. It'll change shape to allow you to focus on something that's farther away, um, versus nearer to you. Okay, more on that in a moment, or not in a moment, but in a little while, probably in the next narration. Okay, so the retina. So this is now we're looking at a piece of the retina, okay, right here, okay. And so let's take it step by step. The light entering the retina triggers photochemical reactions in rods and cones in the back of the retina. Okay, so we have this single cell, okay, of rods and cones, okay, named because that's what they're shaped like. The rods look like rods, the cones kind of look like, in a way, sort of like, you know, ice cream cones or something like that. You can see it bulges out. Okay, and notice that the rods and cones are actually in the back of the retina. Okay, and there's just one layer of them. Remember, I mentioned that in previously when I said, you know, hey, we see in 3D, but really there's just a flat screen. Okay, which is the back of the retina. In any case, that light can affect the rods and cones. It creates a photochemical reaction. And that chemical reaction in turn activates what are called bipolar cells. Bipolar cells basically are bipolar because they're hooked in both directions. They're hooked into the rods and cones. They can receive stimulation from them, and then they in turn stimulate ganglion cells, okay, which are really neurons, okay. And those neurons, the axons of them, okay, basically converge to form the optic nerve, a bundle of axons coming from the ganglia in the eye, okay. This nerve transmits information to the visual cortex via the thalamus in the brain, okay. So enters, chemical reaction, enters, triggers photochemical reactions here, activates bipolar cells, activates ganglia cells, okay, and that information, the electrical impulses, the neural impulses that are created, then get on to the brain, okay? Okay. That's what we were looking at, just a portion of the retina. Okay, so photoreceptors, these rods and cones. So when light reaches the back of the retina, it triggers chemical changes in the receptor cells, as we've seen, called rods and cones. Okay, and then we see they send messages to the ganglia and bipolar cells and on to the optic nerve. Now, rods, okay, help us see the black and white actions in our peripheral view and in the dark. Okay, rods, there are about 20 times as many rods in our retinas, okay, than there are cones. Okay, cones have the task of helping us see sharp, colorful details in bright light. So as we're going to see, okay, rods are basically what we're using for night vision. Okay, cones are what we're using to get acuity and to see color and to see detail, day vision, if you will. So here's a nice little summary table. There, you got about 6 million cones in each retina, okay, each eye, and 120 million rods, okay. They're located in the center of the location of the retina. The cones tend to concentrate in the fovea, in the center of the retina, whereas the rods go around. Remember, I said it goes from the top to the bottom of the, so the periphery, that's where the rods are concentrated, okay. A lot of sensitivity in dim light by the rods, much less sensitivity in dim light by the cones. Color sensitivity, rods are high. I'm sorry, cones are high, rods are low. Detail sensitivity, cones are high, rods are low. Okay. How do we see this? Okay. So let's look at some details about why rods and cones do what they do. So cones are concentrated in the center of the retina, especially at the fovea. So when you want to focus on something, you're going to try to get what you're trying to focus on to impinge upon your fovea, okay? Because that's where we have all the cones. Now the thing about cones is that they tend to have one-to-one connections with bipolar cells, okay? So this one-to-one connection, okay, so each cone is connected to a single bipolar cell, okay? So that one cone can communicate its own information, okay, as can the cone next to it, which is seen just a little bit over from what the other cone is seeing. So because it's this one-to-one, you can get a lot of detail, okay? So that allows great acuity. It allows us to pick up details, okay? Each piece of information, okay, in the visual detail is, and when you've got it on the retina and it's daylight, is basically communicating uniquely to a cone, okay? So we can get a lot of detail because each piece of detail has its own connection, okay, with the bipolar cells, which is eventually going to get that information to the optic, to the occipital lobe, to the visual cortex. Now rods, there's a lot of them, okay? No rods in the fovea, okay? But the thing about rods is that they're not connected one-to-one, okay? They're connected many to ones. So lots and lots of rods converge and connect with those bipolar cells, okay? Which are connected in turn to the ganglia. Don't forget that the ganglion cells. Okay, so why is that significant? Well, it allows a pooling or a massing of stimulation. So you're getting a little stimulation of a lot because it's a dim stimulus. It's dark and it's a very dim light. Okay, but you're able to see it because you're getting a lot of rods are being stimulated by it. Okay, and because a lot of rods are being stimulated by and they're connected to to a single bipolar cell, it allows that information to add up. Okay, it allows you to basically see in very dim stimuli because lots of information is coming about that single stimulus, all focused and massed onto stimulating a bipolar cell. Okay, so cones are very good in day vision because they got this one-to-one connection. And rods are good in night vision because you don't have much light. Okay, it needs to be pooled or massed together, and rods basically have this many-to-one connections with bipolar cells. Okay. All right. A little more on this. Okay, so the photochemicals in the rods and cones are basically what is sensitive to light, okay? So cones have a lot of what's called iodopsin, okay? This is a photochemical. Rods have a lot of rhodopsin, okay? Now, rhodopsin is also found in carrots, okay? It's basically composed of a lot of vitamin A, okay? So remember, your mother or maybe your grandmother or whomever telling you, eat a lot of carrots, it helps your vision. Okay. Well, to some extent that's true because there's a lot of vitamin A in carrots and there's a lot of vitamin A in rhodopsin. Okay, so you're building that up, and so that's where that saying and that little truism comes from. Okay. Now, when you so basically, when you when the light impinges upon rods and cones, okay, the light will eventually bleach out those photochemicals, okay, so that if you just kind of don't look at it, you look directly ahead and you're not moving your eyes and you got just the same stimulation, okay, the stimulus is just going to disappear on you because of this bleaching out, okay. that will occur. But we're moving our eyes and so on. Um, but when you think about it, think about what happens when you're in the you come out of bright light into a movie theater and it's very dark. You can't see a thing. Okay, everything's been bleached out. Okay, by the light, and now there's no more light. Okay, um, and so, but then over time, what happens is you can see better and better. You can find your partner who's already sitting there. You were bringing the popcorn in finally, and everything gets copacetic. Um, that's called dark adaptation. Okay, so basically, what happens when we move into the dark from the light? Okay, the cones adapt by increasing the amount of iodopsin. There's much less light, so there's no bleaching going on, so you can have this buildup of the iodopsin. Okay, and that happens in the first 7 to 10 minutes. Okay, the rods adapt with increased rhodopsin over a longer time period. They become much, much more sensitive because whatever bleaching there was has basically given way, given the dark. Okay, so they become so within the first 7 to 10 minutes after you go into the dark, and the process begins within the first couple of minutes. But by the time we get to 7 to 10 minutes, the rods are actually much more sensitive than the cones. Okay, and that continues on until about a half an hour. Okay, so by the time you've been in the dark, well, don't forget the rods can pick up little amounts of light because of the massing of stimulation, light stimulation. After about a half an hour in the dark, you can detect light about 1/1000th as much as great as in full light. So if something required 1,000 units of energy for you to see in the light, okay, in full light, it only requires 1 unit, if you will, of energy for that to happen. So you become very, very sensitive, increasingly sensitive to um, to light. Okay, so you can't see virtually anything when you first go into the dark, but after 30 minutes, little points of light can be detected, and you have much, much more sensitivity. Okay. So we might have asked, why in cockpits of airplanes do they use red lights? Okay. Well, one of the things with red lights is that you can get the rods to do this adaptation. Okay. So they become increasingly sensitive, and we switch to rod vision. But at the same time, this light keeps the cones basically sensitive. Okay, so that's one of the reasons that tend to see better, see controls better under red light. All right. So the images that we see, okay, of course, are not made of light. They are made of neural signals. The light stimulates the photoreceptors, and that's it with the light. Okay. The images basically are made of neural signals, which can be produced even by pressure on the eyeball. You can press your eyeball in your closed eye, and you can kind of like, quote, see things in there. Okay. So once neural signals enter the optic nerve, they're sent through the thalamus to the visual cortex. Okay, so here we are. The retina is okay, and you can see the optic nerves, and the thalamus being the relay center, getting all that stuff. Okay, visual area of the thalamus, getting all of this over to the visual cortex where it can be processed further. Okay, so how do we turn neural signals into images? Well, some ganglion cells in the eye, and this is fascinating, send signals directly to the visual cortex in response to certain features, such as visual patterns, certain edges, lines, movements. So, for example, in and around the visual cortex of the occipital lobe, you've got these structures which are called which consist of supercells, okay, which have this complexity, this ability to detect certain features, okay. Um, they integrate these feature signals to recognize more complex forms such as faces. So, you know, we actually have supercell structures that that basically facilitate the recognition of visual patterns for faces, okay, for houses, for chairs, for houses and chairs. Damage here, for example, okay, can make it impossible for people to actually be able to recognize faces, okay. So so we often, so another term for these are called feature detectors, okay. You can read about that in a little bit in the textbook because it goes into it a bit more than I will. Okay, so an example of the role of nurture and the nature of perception. So we talk about these feature detectors. Okay, in some ways they are dependent on experience. Okay, so classic studies done with kittens. Okay, so we've got kittens who are raised from birth in an environment that has only vertical lines, okay? No horizontal lines, okay? It's all vertical, okay? And they become, as adult cats, okay, raised this way, they are unable to detect horizontal lines, okay? Don't see them when they're presented, okay? Why is that? Well, we've got feature detectors, okay? We and cats, okay? And feature detectors for lines, for angles, and things like that. And part of the development of those feature detectors depends on experience, okay? It depends on experience, okay? So there was no nurturing, no learning of this because there was no exposure to horizontal lines in the cat's kittenhood, okay? Therefore, they cannot see it. Those feature detectors, those specialized feature detectors, were not did not develop fully or sufficiently. The major example you'll get out of the modules, out of one of the module on vision, is the example of the guy who had been blind either from, I can't remember, yeah, since birth, and then he actually was able to see ultimately, okay, because of some surgery where they developed a technique to whatever his blindness was caused by, they removed it. But he was unable to recognize and configure faces, okay, because that, and there were other impairments as well, but those specialized feature detectors, those supercell structures, okay, for facial recognition had not properly or sufficiently ever developed because he had been blind. Okay. Okay. So I'll also talk a moment about parallel processing. Okay. So turning turning light into the mental act of seeing. We go from light waves to those chemical reactions we talked about, to those neural impulses, to detecting features, to seeing objects. Okay. And one more step, parallel processing. That refers to building perceptions out of sensory details that are processed in different areas of the brain. Okay. So we talked about feature detectors. We talked briefly about, supercells. We talked about portions of the brain that basically develop in the cortex, in the visual cortex, and to basically be sensitive to certain forms of sensory details. Okay, process in different areas of the brain. Okay, but it's all happening in a parallel, if you will, simultaneous process. So we have detectors for color, we have detectors for motion, we have detectors for form, we have detectors for depth, okay? And all of those aspects of the visual stimulus are being processed in parallel. So we don't build our perceptions, or what we see. We see it, okay, because all of those steps were taken in a simultaneous parallel processing way. So here's a summary of basically what we've been talking about. So we have a scene, okay. We have the retinal processing of it, that we've been through, okay. We have the feature detection. The brain's detector cells respond to specific features, edges, lines, angles. We have that parallel processing. All that stuff's going on simultaneously, and then it gets combined and integrated, okay. And ultimately, that combination and that integration results in a recognition. The brain interprets that constructed image, okay, it's continuously being constructed, okay, in this parallel processing way, interprets it based on information from stored images that already exist, okay. And so, and that goes back to how our experience may affect how we perceive things. Okay, even at the sensory level, we're integrating all this information, and the recognition involves some comparison with already known objects and stimuli. Okay, a little bit on color vision. Okay, and then this will be our last topic here, and then we'll move on in a subsequent narration and talk about how it all gets put together in terms of the perceptual end of it. We've already been through some of that, but might go through some more. So the three color theory of color vision, okay, refers to the idea that if we look at the cones, there are three kinds of them: those that are sensitive to red wavelengths, green, and blue. Okay, and all the colors we perceive are created by light waves stimulating combinations of these cones. Okay, combinations of the three sets of cones sensitive to different areas of the color wavelength, of the color spectrum. Okay, so color blindness, okay, people who are missing red cones or green cones have trouble differentiating red from green, and thus would have trouble reading the numbers to the right here. Okay, you look, it's 45. It would be hard for someone who's colorblind in this way to see, that number. So following up on this idea, or this number actually, refers to the neural. There's this theory known as opponent process theory. That refers to the process of perceiving white as the opposite of perceiving black, yellow versus blue, red versus green. That there are sort of opponent processes. Okay, and so. That has some implications in the sense that, we've often experienced visual after effects, and that sometimes involves, you focused on something, so the cones get bleached out, okay, and so things kind of disappear, but the cones that got bleached out were the ones that were, if yellow cones got bleached out, those that are sensitive to yellow, then basically you become less sensitive to yellow, and what gets magnified, okay, is the opposite color, namely blue. Okay, so I'm going to end this little narration, and I encourage everybody to, we want to get the main points here, of course. But the best way to do that and to get further explanation, of course, is to go to the textbook and read carefully, being guided by the main points that I've hit on. Reading this more carefully as you have more time, because it's pretty much nicely represented in the modules in the textbook. All right, so let me say goodbye. Okay, well, I'm not going to say goodbye yet. We're going to do a little demonstration, okay? So what I want you to do, okay, is to stare at the dot in the middle for at least 30, 40 seconds. And so I will, so start doing that now, and I'll kind of count that time off, and um, we'll see what happens. Keep staring. You're still staring? Okay. What do you see? Or what did you see? It's now faded out. You should have seen red, white, and blue. Okay, a flag of kind of like the Union Jack. Okay, except red, white, and blue. I'm still seeing it a little bit. And why did that happen? Okay, well, the other thing you should have noticed as you were staring is that there might have been some bleaching where the whole thing might have just sort of started to fade away. Okay, and then when we ended this, okay, you should have um, seen red, white, and blue because you bleached out the yellow, okay, by staring, okay. You bleached out the green. You bleached out the black, okay. So if that got bleached out, the opposite color, should have then become more, should have become stronger, okay. So now when we flip it over, we go to the next slide, you're seeing red, white, and blue instead of um, green, black, and yellow. Cool, huh? All right. So that's it for now. And we will talk to you next time.